Hello dear students, welcome again to the tetrahedron chemistry classes. So as you can see, this is my fourth lecture on the molecular orbital theory, and in today's lecture I will discuss the molecular orbital diagram, or you can say the correlational diagram of the oxygen molecule, as well as I will also discuss the molecular orbital diagram, the magnetic properties, the bond order, right, and the bond length of the other oxygen ions like O2 positive, dioxygenyl positive, right, and basically dioxygenyl cation it is, and then your superoxide and then your peroxide. I'll discuss all the things today, and the lecture is going to be very important for any competitive examinations, right? So for the beginners, I'm going to discuss the things from the pretty basics, right? And if you are coming here for the first time and watching this video for the first time, it is my suggestion to watch the earlier 3 lectures as well, and for which I am giving you the link in the description box. So for oxygen atom, you know, when you have the oxygen, it is having the atomic number of 8. If you write the electronic configuration, then it would be 1s2, then you have 2s2, and then you have 2p4. So this is the electronic configuration of the oxygen atom, and definitely when you are going to discuss the diatomic molecules, 2 such oxygen atoms would be there, which will the atomic orbitals of these 2 oxygen atoms will combine to give you the molecular orbital diagram. Okay, so since the space is very limited in my on my screen, so what I'll do here, I'll discuss the things or the bonding starting from the TS orbitals, right? So 2s of this oxygen atom and 2s of this oxygen atom, while I'll not include the 1s atom of the oxygen atom because they are the core electrons. They do not affect the things like the magnetic properties and your say bond order, right? So they are not very important when it comes to these 2 parameters. So it will not make any difference whether you start your molecular orbital diagram from the 1s atomic orbitals or you start from the 2s atomic orbital. For the space problem, I'll discuss the diagram starting from the 2s orbital of the oxygen atom. So for this, what you will do here, first of all, you will take just like that this particular axis here, and in this particular axis your energy is going to increase. So energy is increasing here, so I'm writing energy. Okay, and after that what you will do, you will divide your page into the 3 different columns in order to write the things more correctly and more smoothly. Okay, just like that I'm doing for you. And in the first column you will write the atomic orbitals of oxygens. So I'm writing here AOs, where AOs stands for the atomic orbitals, AOs of oxygen atom. And again, then I write here again atomic orbitals of oxygen atom, and in the middle I'll write molecular orbitals of O2 oxygen molecules. Okay, so see what is the basic feature or salient feature of the molecular orbital theory. That means the first feature is very important. The atomic orbitals combines to give the molecular orbitals, right? If you are watching video for the first time and you are very beginner here and want to learn this molecular orbital theory right from the basics, so please go through the earlier lectures, because it is always possible that various things you may not be able to grasp the correctly here from this particular lecture, especially if you are beginner. So it is mandatory or necessary for you to go there. So I am writing the electronic configuration in that manner. So this is my 2s atomic orbital of oxygen atom, and here I am having my 2p orbital of the oxygen atom. These 3 I have drawn here. Since this is another oxygen atom, so I am writing the electronic configuration 2s here, and similarly in this particular configuration the 2p orbital is also here, so I am writing 2p here. Okay, so this is also 2p. You may consider any orbitals like that. Say this is your px, the first one, this is py, and the third one is the pz. So here again I am writing px, this is my py, and this is my pz molecule. And if you count the total of number of the electrons here, you can see 4 and 2 6. That means you have to fill these 6 electrons in the atomic orbitals of the oxygen atom. So this is 2s2, and then you are having 2p4, 1, 2, 3 and 4. Similarly, I can fill 6 electrons here also, 2, 3, 4, 5, 6. Beginners can focus on the filling of the electrons. How I am doing actually? I am following Hooke's rule of maximum multiplicity. Okay, that's why I am filling these electrons in that particular manner. So the first very important feature is that these two atomic orbitals will combine to give you the molecular orbitals, right? So here I am drawing these two molecular orbitals, just like that. Of course, one orbital will form here and another will form here in that case. Since these are the two s atomic orbitals and these atomic orbitals are cylindrically symmetric along all the axes, so whenever s orbital and s orbital combine, they will produce they will always produce the sigma bond. So here this is your sigma bond, okay, and more specifically it is sigma 2s. If you want, then you can write sigma 2s like that. And definitely the other one would have the higher energy, which is the anti-bonding one. So this is sigma 2s anti-bonding. And you know, when you draw the molecular orbitals, it is very, very important to write their symmetry as well. Okay. So please remember, your s orbitals are always G-rayed in nature. So I am writing G here. This is sigma bonding G-rayed, and anti-bonding sigma is always G-rayed. So if you are watching video for the first time and you are not able to understand the G-rayed and the un-G-rayed things, so you can definitely go for my earlier lectures. Here I cannot waste too much of time to explain the things again and again, but in my earlier lectures I have explained all these things in the pretty much detail. Okay, and then these are your 2p orbitals, so they will combine and they will form another after combination they will form these molecular orbital. And for the oxygen atom especially, you should remember the very important thing, the energy of the 2p orbital, the energy of the sigma, right here, this is where I can write sigma 2p z here. So in that case, again you can notice one thing, for diatomic molecules which are linear, which are having the linear shape, so their molecular axis is basically the z axis. So z orbitals basically form the sigma bond here, and the other two will form other two px and the py will form the z orbitals. Again I am discussing these things, but though I have discussed all these things in my earlier lectures. So here this is my another two orbitals. I am writing in that manner. Say this is your pi 2px and this one is your pi 2py. Okay. When you have formed the bonding molecular orbital, then definitely your anti-bonding molecular orbital would also be there, and the orientation of the anti-bonding molecular orbitals would be like that. Let me draw it little bit correctly. It is very difficult to write or to draw the diagram by using this particular pen. Okay, so then here you will have your sigma anti-bonding 2pz, and these two are pi anti-bonding 2px, pi anti-bonding 2py. When you put asterisk over the molecular orbital, then it represents the anti-bonding nature. And again, it is very, very important to write their symmetry as well, whether they are centrosymmetric or not the centrosymmetric. So sigma 2pz orbital is always here centrosymmetric, so it is G-rayed, while this pi orbitals are un-G-rayed. So in the superscript position you can write u for the pi orbital of the p, right? There's sigma pz is your G-rayed, while your pi and px and pi 2py, they are unGrade one, and the opposite is true for the antibonding orbitals. Your antibonding orbitals, these are the Grade ones. So I can write Grade here, this is Grade here, and sigma 1 is unGrade. It is very important to write the symmetry because they explain the various things in the ground state spectroscopic term symbols. It is very important, and for spectroscopic properties as well, it is very, very important. So this is how you can construct the molecular orbital diagram of your oxygen atom. Now you have to fill these electrons, 2 and 3 here, 4 and 3 and 4 are 4 to 6. So 4 to 6 electron this, and 4 to 6 electron this. So total of 12 electrons you are having, and you have to fill these 12 electrons into the molecular orbital. So you will follow the above principle, and what it says, the lower energy molecular orbital will be filled first. So 2 electrons will go here, because like atomic orbitals, your molecular orbital can also accommodate maximum of the 2 electrons. So you can put 2 electrons in the any molecular orbital. Similarly, 2 will go there, and then again 2 will come here, just like that. So 2 to 4 to 6, and then Hund's rule of maximum multiplicity you will follow, 7, 8. This is how you can write, right? 2 to 4 to 6, 7, 8, and then 9 and 10, and this is 11, this is 12. So this is the molecular orbital diagram of the oxygen atom. Now you can see, you can calculate the bond order for this one. So what is the formula of the bond order? Bond order equals to number of electrons in the bonding molecular orbitals minus number of electrons in the anti-bonding orbitals divided by 2. So how many numbers of electrons are there in the bonding molecular orbital? Bonding or molecular orbitals are those which are not having the asterisk superasterisk. So this is lower in energy, this is bonding. So 2 electrons are here. This is another bonding, 4. This is another bonding, 6. This is another bonding, 8. So total 8 electrons, 2 to 4 to 6 to 8. Total 8 electrons are present in the bonding molecular orbital. So you'll write 8 here. And in the anti-bonding molecular orbital, you can see this is the anti-bonding orbital. 2 electrons are here, and these 2 are also the anti-bonding orbitals. So 2 are here. So total 2 plus 2, 4 anti-bonding electrons are there. So you'll write 4 here. And if you divide this by 2, you will get 2. So what it indicates? It indicates that two oxygen atoms are connected with each other with the by this double bond only. So bond order of this oxygen molecule is 2 here. And then you can go for the magnetic properties. Magnetic properties of the oxygen. So I am writing magnetic properties. And you know, in the molecular orbital diagram, when you have all the paired electrons, then your species is diamagnetic. But if you find any one electron or more than one electron unpaired in the molecular orbitals, then your species is the paramagnetic. So you can see here in the pi antibonding molecular orbitals, you are having 2 unpaired electrons. One is this one, another one is this one. So 2 unpaired electrons are there. So that means it is paramagnetic in nature. So straightforward you can write paramagnetic. So this species is paramagnetic, right? And when it is paramagnetic, then definitely you can calculate the magnetic moment of the species. The formula of the magnetic moment is equals to mu under root of n times n plus 2, where n is the number of unpaired electrons. So number of unpaired electrons in this molecule is 2. So 2 times 2 plus 2, that means 2 to 4 under root of 8. This is the magnetic moment of this particular species. This is how you can very beautifully construct the molecular orbital diagram. And one thing which I forgot here, it is also good if you write like this, not to the scale, because we didn't take any graph or any scale to define the energy, right? So it is always better to write the not to the scale over there. So this is the molecular orbital diagram of the oxygen, and if you want to write the electronic configuration of these molecular orbitals, then you can write just like that. sigma 1s G rad, this will have 2 electrons. This will have and this will have lowest in energy. However, I didn't draw the 1s or 1s diagram, but I am writing the configuration. 1s molecular orbital I didn't draw, but I am writing the configuration for this one. Okay. Then your sigma 1s anti-bonding, it is G rad. Okay. Sorry, it is un-G rad. And if you want, then you can put star also over there. 2 electrons are here. And then your sigma 2s, which is the G rad one, and again it is having 2 electron. And then next high energy is for sigma 2s un-G rad, that is anti-bonding, again it is having 2 electrons. And then you are having, you see how I have written all these things. Say this is 2s G rad, so this is your 2s G rad with 2 electrons. This is 2s un-G rad with 2 electrons. So this is 2s un-G rad with 2 electrons. After that you are having this pz G rad, sigma 2pz G rad you are having in that case, in case of the sigma bond, right? So next higher energy orbital available is what? Sigma 2pz G rad, and it is also having 2 electrons. And after that you are having pi 2px, it is un-G rad having 2 electron. And next is pi 2py un-G rad, it is also having 2 electron. And then you are having pi anti-bonding 2px G rad, 1 electron, and it is having equal energy with the equal energy like your 2px anti-bonding, sorry, 2py anti-bonding, it is again G rad, so 1 electron. And next is the filling of these. You can write like that. I am not having space, so I am not writing this. So this is the energy order as well. So this is the complete diagram of your oxygen molecule. Now we can see what happens if I draw the molecular orbital diagram for the cation and other things. So diagram is already I have drawn, and now I'll discuss the other things. I hope this is quite clear to you. Now I am going to form this O2 positive dioxygenyl cation. So O2 positive is basically your dioxygenyl cation. Now see, when you put this positive charge here, it indicates the deficiency of the 1 electron. That means your molecular orbital diagram would be 1 electron less. So how I can remove 1 electron from it? So definitely the electron would be lost from the higher energy orbital. So I am removing this orbital from here. Okay, there is no problem. Clear? And of course, if you want, then you can remove 1 electron from here as well. So I was having 1 electron less. So definitely after that, any one of them you can write 2p3. So you are having 1 electron less. So what is the meaning of that? You are, see, from where you have removed the electron? You have removed the electron from the anti-bonding molecular orbital. So when you calculate the bond order of this one, so you will subtract 1 from this 4, because now your anti-bonding orbitals are only 3, 2, and this is the third one for your O2 positive cation. So very beautifully what you can do, you can remove this here, okay, and then again I will change the formula as well. So now what I will do here, I will write 3. So 8 minus 3 is 5, this is 5 by 2. So the bond order is 2.5 for O2 positive. Still the magnetic properties would be your paramagnetic, because again I am having 1 unpaired electron, but 1 electron pair will give you the less magnetic moment, because magnetic moment would be less when you have the less number of the unpaired electron. So now here only 1 unpaired electron is there. So 1 plus 2, that is 3. Under root of 3 is the under root 3 is the magnetic moment of this O2 positive. And the energy order, how the energy order will you will write, you will remove again one electron from here, like that. Okay, so this is how you will form this this thing. This is very, very important. Please remember, it is very, very important, and this will also affect the bond length as well. So how the bond length? So let me give you little data. However, it is not very important to mug out all the data, but it is good if you can remember this. When you have the oxygen molecule O2 molecule, then this bond length is roughly 121 ppm. It is picometer. Okay. Now you can see here, see, bond order is inversely proportional to the bond length, right? So I need some space, so I am removing this one. And again I am writing here, please remember, very important, bond order is inversely proportional to the bond length. So I am writing in that manner. I hope it is quite clear. L, this is bond length, right? This is L. So here you can see, in case of your O2 positive, right, in that cation, your bond order has increased. In that case, bond order was 2 earlier, right? For this, BO was 2. Now for O2 positive, your bond order has increased, right? Your bond order has increased. That means this will have the more bonding interactions. Since you have removed electron from the anti-bonding orbital, then definitely anti-bonding interactions will decrease and your bonding interactions will be higher. When your bonding interaction will be higher, definitely it will reflect in the high bond order, and the bond length would be shorter than this time, right? Because it has increased and they have the inverse relation. So for this cation, this bond order is little bit of the lower side. It is bond length, I am writing BL, it is 112 picometer. 112 picometer for O2 positive. Please remember, it is very, very important. This is how you can draw the molecular orbital diagram of the dioxygenyl cation as well. Now if you want to draw the molecular orbital diagram for, say, your superoxide ion, right? So I am writing here superoxide molecular. See what I can do, I can shift it here and then I can remove this and then I can write superoxide, right? Superoxide is O2 negative. Superoxide is O2 negative. Please remember. See, it is very, very important to learn the formula of the ions as well, because sometimes you may have difficulty in drawing the molecular orbital diagram if you don't know what is the formula of the superoxide, what is the formula of the peroxide. Okay, so how I can draw the molecular orbital diagram? So for this, first of all, I'll come to my initial diagram of the oxygen molecule. So initial diagram of the oxygen molecule like that. This was the oxygen, right? And I'll remove rest of the things here because this may confuse you. So I'm removing this, and again this is also I am removing like that. Okay, and I am also putting my electron back here. This was the original condition of your oxygen. Now you need to construct the molecular orbital diagram for your this negative ion. Now this negative charge represents the excess of the one electron. So you need to put one extra electron. This was the earlier position, and say you have put it one extra electron here, and that one extra electron will go either in the px or in the py. Okay, so this is this is the molecular orbital diagram of your superoxide ion. If you go for the bond order, so number of the bonding electrons would remain the same. That means they would be your 8. And in the anti-bonding orbitals, now you are having 5. How 5? You can see here. See, first of all, bonding 2 to 4 to 6 to 8, which I have written here. These two are the anti-bonding electrons. Then 3, 4, 5. 5 antibonding electrons, and this should be divided by 2. Okay, that means 3 by 2, so it is 1.5. So bond order here is you are decreased, right? Bond order has decreased. So definitely when bond order has decreased, the bond length of this Bl I am writing, bond length of this O2 negative would be little bit should be on the little bit higher side. So for O2 negative, if you check the bond order, it is 125 picometer. 125 picometer, which is quite obvious when the bond length decreases. When the bond order decreases, as you can see here, it has decreased from 2 to 1.5, so it has to increase, so it is 125 picometer. It is reflecting here. Now if you think about the stability, definitely this would be less stable because you have added one extra electron in the antibonding orbital. That means antibonding interactions are increasing. This will decrease the stability, which is reflecting in its bond length as well. So if you want to change the electronic configurations here, so again you can put one electron here. So this is your this is energy order for the these orbitals, right? Molecular orbitals. I hope this is quite clear, right? Next, what you can do, you can draw this for peroxide as well. Molecular orbital diagram for peroxide ion. Peroxide, it is very easy to remember. If you know the formula of the hydrogen peroxide, which is H2O2, then it is very easy to you to construct the molecular orbital diagram. See, 2 negative would be there. So now it is 2 negative, that means I am having one extra electron, so I am putting one extra electron here. So one extra electron I will put here again. So what, how it will affect the bond order? Now you are having anti-bonding electrons, total 6. So write 6 here. How 6? See, 2 to 4 to 6. However, bonding electrons will remain changed, they are not affecting, right? So that means 2 by 2. This is basically your 2 by 2. So let me remove it. So writing is 2 by 2, it is 1. So again you can see the bond length, bond order further decreases. That means, and then you can see the bond length of this your peroxide as well. So this is the bond order has decreased drastically, and it went up to 1. So definitely your bond length must be higher because they have the inverse relation. So for peroxide it is having the 49, it is having the 149 picometer of the bond length. So if you want, then you can quickly summarize all these things. So how you can quickly summarize all these things? Say for example, you are having your dioxygenyl cation O2 positive. This is your O2, and this is your superoxide, and say this is your peroxide. Okay, oxygen, you know, it is having the 16 electrons in total, so definitely it will have the 15 electrons as you have seen already, and this will have here 17 electrons, and this will have here 18 electrons. Okay, and if you go for the data of the bond order and the bond length, then you will see in that case of this your O2 positive, bond order was 2,5, and in that case your bond order is 2, in that case your bond order is 1.5, and for peroxide it is 1 only. Since this bond order of 2.5 is the highest one, definitely it should have the lowest bond strength and the maximum stability for this cation, and it is of 112 picometer. Since now the bond order has decreased, so bond length must increase for the oxygen molecule, and for oxygen molecule the bond length is the 121 picometer. Now you can see from oxygen to the superoxide your bond order has decreased. That means bond length will further increase, and for this superoxide ion it is having the value of the 125 picometer, and for your peroxide your maximum your lowest bond order has achieved, which is on the order of the 1. So its bond length must be on the highest side, so it is of 149 picometer. So this is how you can decide the magnetic nature, bond length, bond order, and the stability of these species, right? I hope you understood the lecture well. If you didn't understand certain things, then you are beginner, so you can go for my earlier lecture to understand the things, right? I have made a molecular orbital theory in the pretty much detail in my earlier lecture as well. So in the next class I'll discuss the fluorine and the other ions as well, right? So that is for today. Thank you very much.